from the chart here. So the first thing we have to decide is what country are we actually talking about, and how much energy do people in that country use on average. And for that, you can look up on Wikipedia. I have a web address here at the top of the slide. Unfortunately, the numbers that are there on Wikipedia are a little bit old. And I actually encourage, should be better now. So I encourage some of you to go into Wikipedia and edit this table, and instead of this 2014 column, make a new column for 2017 or 18. I believe I put over there on the right-hand side, there's the different sources where you can get this information. I actually looked up this information before, and I think it's the easiest way to get it is in the World Bank database. There's online on the web, there's a World Bank database with the amount of energy used per country or per citizens in those countries. And then you can basically just copy those data into Wikipedia. There's a little bit of formatting that is needed, but I encourage some of you to do that so that we can have Wikipedia updated with newer data. And last time I looked, I think it was 2017 or 18 numbers are now available for free. If you're willing to pay, you can get even newer numbers. All right, so I should go back. So you can see I have circled with a green box the Netherlands because I wanted to use the Netherlands energy consumption as a number. But of course, you can choose any other country, and you could also find the updated number from today. And then you also need to find out like how much energy do we get when we fission thorium. So actually we don't fission thorium. You probably know from some of the other talks that first we need to convert thorium into uranium-233 inside the reactor. And it's a matter of fact, it's actually uranium-233 that is fissioned, and so the energy of the fission process comes from uranium-233. And there's a wiki page here that I've shown the URL at the top of the slide, where you can go, and it says on that slide, in the green box there, it says that for each atom you fission, you get 197.9 mega electron volts. And most people don't know what mega electron volt is, but don't worry, because it also, they have converted it here to terajoules per kilogram over in the right side of the green box. So this is what we will use, and I will even show you later how to calculate this conversion from mega electron volt to terajoule per kilogram. And what I also want to point out here is the table below that green box. It's also on that web page and on several other web pages, and from there you can see that the energy when you split the atom actually comes from a little bit different sources. So the two fission fragments, so when you split the atom, you get two fission fragments of new atoms, and they have kinetic energy because they have speed, or they're moving through the whatever material they're inside. In a reactor, they're moving through the salt, and that movement gives rise to some heat, and that is most of the heat. So that is 168 mega electron volt. And then you can see that there's a little bit, there's some gamma rays and beta rays and some other things that also contributes a little bit to the energy. So now we have found the numbers that we need in order to make the calculation. I have made some on the right-hand side here on this box or this page. I've made shown the Google searches that you can do to actually get some of the numbers we need for the conversion. So the first one is uranium-233 molar mass. So if you search that on Google, it gives you right away the molar mass of uranium-233 because you need that in the calculation. And a little bit further down, I've also Googled the density of thorium. You do that, and then it gives you the density of thorium metal at 20 degrees Celsius. So those are some of the numbers you need for the calculations. But so in the first line up there, I take the number from the Netherlands average energy consumption per year per person, which is 193.43 gigajoules per year. And then I assume that a person will live an average 100 years. And so that makes an easy calculation, and this is how I get the 19,343 gigajoules. So that's the amount of energy we need for our entire life. And I will come back and explain a little bit more about that, but that's the number we will use now in this calculation. And then in the next line, I have the number from the page just before this, where this 197 mega electron volts was converted into gigajoules, or sorry, terajoules per kilogram. But now in this slide, we are calculating in grams because that's easier. So we convert it to gigajoules per gram instead, and use that in the calculation. And then on the third line, you can see that I take the amount of energy I need and divide it by the amount of energy created per atom that is split. And then from that, I get that I need 236 grams of uranium-235. All right. But now it's a thorium ball. So we have to convert those 236 grams into thorium because that was uranium. And there's a slight mass difference between uranium and thorium. So this is what I have inside the parentheses there. So I multiply by the thorium molar mass, and then I divide by the uranium-233 molar mass. And then I get that we need 235 grams of thorium. So that's the thorium that you have to dig out of the ground for your entire lifetime of energy if you live in the Netherlands. And then now we need to convert that 235 grams into how big a ball is that. And for that, we need the density. That was the 11.72 grams per cubic centimeters. And then we do the conversion, the simple division, and then we get that the sorry about that. I have to put it on silent. All right, so that means that we have a total of roughly 20 cubic centimeters. And now we need to convert that into a ball shape. And for that, again, we Google what is the volume of a sphere, and we get this formula that a volume is equal to 4/3 times pi times the radius cubed. And basically, we need to convert that equation so that we get the radius and put the volume under the cubic root. And then I put in the 20 cubic centimeters, and out of that formula comes that the ball radius is 1.685 centimeters, and that gives us a ball size of 3.37 centimeters. So that's the ball size if you live in the Netherlands. I've made a number of assumptions here that I will explain, but this was the simple explanation for how to calculate the size of the ball. And if you look at the fourth line there, where I convert from thorium to uranium, there's a very small mass difference between those two numbers. So even if you forget to make that adjustment, you more or less get the same ball size. So it's the line number 4 is not really important at all. But now we will talk about some of the things that I didn't say. For example, in line number 2 on this chart, we said that we have 81.95 terajoules per kilo. And how did we get that number? And we saw on the page here that it was in the green box. It came from this 197.9 mega electron volts. So how to make that conversion? And I'll just quickly explain that here. So to make that conversion, again, we need to Google a few numbers. First of all, we need to know the molar mass of uranium. We also did that on the last slide, but we need that here. And then we need to convert mega electron volts into joules. And of course, Google can help us with that as well. And we actually can put in the 197.9 mega electron volts on Google, and then it will tell us that this is equal to 3.17 something to e to the minus 11 joules for each fission. And then now in the first line of the calculation down there, we just have to multiply the Avogadro's number, which is the number of atoms per mole, by the molar mass of uranium-233, and then we get the number of atoms per gram of material, and that is 2.584 e to the 21st. So lots and lots of atoms in 1 gram, and then next to that we have to multiply it by the number of joules per atom when it fissions, which you can see there from the arrows where I'm getting those numbers from. And this is how we get to this number, 81.93. And then first we get it in joules per gram, but then of course we have to convert it into terajoules per kilogram. And that's what you can see that the last Google box down there at the bottom, you can actually get Google to convert that directly for you if you don't want to do the math with the tera and kilo and so on yourself. So this was the explanation of how the conversion in this green box here on top of that table was made. And now we get a little bit more into details. Let me just go up here again, because now here in this first calculation we made and found the size of the ball, we assumed that we could consume all the uranium, and we assumed that we could convert all the thorium into uranium, but that's actually not possible inside a molten salt reactor, a thorium molten salt reactor. And now it becomes a little bit more complex. Now we need to find out how much of that thorium can we convert. And so in this chart here, you have at the top a blue box saying thorium-232. This is your input material. And then when we just talk about this in general public, we say that it converts into uranium-233, and then we fission uranium-233 and get the energy. But in nuclear science, it's actually a little bit more complex, because it's not only uranium-233 that fissions and create energy. It's a little bit more complex. But so I've tried to draw some arrows here. Let me see if I can get this right. So the most common route is this route with the green arrow that I call A, where thorium-232 is converted into thorium-233 and then protactinium, and then it decays down to uranium-233, which then fissions. And you can see there in the box that it says that 87.3% of that uranium-233 will fission. So not all of it. And you can also see up there at the top in the blue box that it says that 1.7% of these are all statistics given at a certain neutron spectrum in a reactor. So you can see already the thorium-232, a small amount of that, namely 1.7%, will fission. And then you can also see further down that some of that uranium-233 will actually take the D route, the green arrow with the D, and it will convert into uranium-234, which will also fission. A small amount of that will fission. And there's also this other route, the route B, where it actually, you can see that it starts out with only being 0.3% of the thorium that takes this route, and then this further diminishes further down. So that it's a very, very small amount of the material that takes route B, but it is possible, and it does contribute a little bit. And then finally, there's this route C, where the uranium-233 goes, it captures a neutron, and then it turns into uranium-235. It actually has to capture 2 neutrons to get there. And then uranium-235 can also fission with a high probability of 77.1%. So all this is very complex, and it's probably boring to look at, but I've made in this I've shown 4 errors, but there's actually more than those, but just with much, much smaller probability. So if you look at these calculations in the top right of this slide, you can see that route A is responsible for 85.3% of the fission, and route A plus C is, so if you first take route A and then the fission doesn't happen there, but it then takes route C, then 9.2% of the thorium will end up as uranium-235 and fission there. And then if you take route A plus B, then 0.4% will fission there. And if you take route B, only 0.1% of your thorium will fission there. And then, of course, there's the thorium itself that could fission right away, where it's only 1.7%. So if you add all those up, you get to 96.7%. But in all fairness, all these numbers depend on your reactor, the way you've constructed your reactor. It depends on the neutron spectrum in your reactor, and it depends a lot on the different materials that is used for the construction. And even these numbers here are questionable because they come from something called nuclear data files, and they are not always 100% correct. So it depends a little bit on which set of data files you actually depend on. So this was just to explain that maybe we can only convert roughly 96% of the thorium into fissionable material. And then I've also done this calculation. You can see on the third row, we had Netherlands. That was the number that I used before, where we get to 3.4 centimeters. But if you take other countries, for example, we all know that the US uses a lot more energy per citizen than we do here in Europe on average. So the ball size in the US would be a little bit bigger. And you can also see that the Netherlands has a lot of production of products that uses a lot of energy. So therefore, the Netherlands uses more energy on average than, for example, Germany or Denmark, which is other European countries. There's not that much production going on in Denmark. We import most of our products, and this is basically why we use a smaller, we have a smaller energy footprint. So that brings me to another discussion. You can also see that China uses quite a bit of energy, but in reality, China exports lots and lots and lots of production to other countries around the world. And if we were to only look at the amount of energy used for China's own consumption, that number would be much smaller. Maybe not as small as India, but it would be closer to India than to Denmark, for example. And this is because those numbers that we discussed in the beginning, which you can find on the World Bank and which you can find on Wikipedia, those numbers are not taking into account where the products that are consumed are manufactured. They just talk about the amount of energy, that means oil and gas and coal, that is consumed in each of those countries. Of course, also hydropower and wind and solar, but they do not take into account when products are manufactured in one country and then shipped to another country, which of course completely screws up the understanding or the comparison between countries, because European countries in general get a lot of products that are not made in Europe, and the same for the US. So the actual consumption of energy in those countries are much bigger than what these tables show. So therefore, you could also say that it's not true that the ball is 3.4 centimeters in the Netherlands. It's probably more like 4.5 or maybe even 5 centimeters in diameter. You can also see here, for the fun of it, I didn't mention that, but Iceland is one of the countries in the world that uses the most energy. And the reason for that is because they have extremely cheap energy from the geothermal energy. So they basically get hot water completely for free, and they get electricity at very low prices. So they basically only consume expensive energy for cars like gasoline and diesel. So this is why Iceland uses so much energy. Also, some of the energy-intensive industries like aluminium industry are on Iceland. So that also the reason why they use a lot of energy per. So you can see Iceland is a small country with something like 100,000 people, or maybe 200,000, I can't remember, but it's something like that. And then if they have a huge aluminium industry that uses huge amount of energy, then of course it easily gets out of whack.